Alright, welcome back, and today we are going to be looking at how to predict redox reactions, specifically using our 5-step method that we're going to go over. So the main thing to remember is that every single time we mix stuff together, if a redox reaction occurs, it is a competition for the electrons. So the electrons are going to get transferred from the oxidizing agent to the reducing agent due to the stronger force of attraction. And one thing you do have to remember as well is that not all reactions are going to be redox. You need to look for a change in specifically charge. Now, for the most part, when we're just dealing with elements and ions, simple monoatomic ones like aluminum, silver, everything like that, we have those little rules about we know metals generally lose electrons, so they're good reducing agents, and so on. But for the polyatomic ions, we're going to have to search our table to determine if they are a reducing agent or an oxidizing agent. So what that means is we're going to have to refer to our table of selected standard electropotentials or our reduction half reactions here. So remember, if it's on the left-hand side, these are the oxidizing agent side, and our strongest is up at the top left. And of course, on the right-hand side is our reducing agents, and as we go down, we get our strongest reducing agents down to the bottom right-hand side. So there are a handful of things that can be oxidizing agents and reducing agents as well, so you do have to be careful about, of course, when you find them, but there's only 4 on our charts, which is iron 2 plus, tin 2 plus, chromium 2 plus, and of course water. So that means when we're predicting redox reactions, we're finding oxidizing agents and reducing agents. If you do see any of these right here, just be aware that they do show up twice. Now, of course, if we are trying to figure out what is going to react, we do need to kind of go back a little bit and take in a part of a little Chem 20 when it comes into listing entities. So just remember, when we're listing stuff and trying to figure out what is reacting, if you see the word aqueous or solution, it means that water is going to be present. All right, so you want to look for those words. If they do not show up, then we can assume water is present. If you see the word acidified, not acidifies, acidified means that we have the hydrogen ion present. And the word basic means we have the hydroxide ion present. Now also, if you're given molecular compounds or polyatomic ions, remember, don't dissociate them. So if you have something like methane, if you put it in solution, it's going to stay as methane. If you have the phosphate ion, it's going to stay as the phosphate ion, and so on. The only time we dissociate something is highly soluble ionic compounds. And of course, our strong acids. So there are, if you remember, there's 6 strong acids. Now, in Chem 20, you did have to have those memorized. Now, if you don't really feel like memorize them, if you just go beyond page 7 here in your data booklets and go to page 8, you will notice it's going to look something like this. Now, above the hydronium ion here, which we know is a strong acid, you'll notice that there are 6 acids listed at the top. These are actually our 6 strong acids. And their chemical formula here is with them as well. So whenever you're given acids or strong acids, we do ionize them 100%. So it's going to be these here. Remember, if it is a weak acid, like any of these here, like phosphoric acid, we do not ionize it. It's going to stay as H3PO4 or whatever. Now, for oxidizing agents and reducing agents that are in combination, all ions must be listed. So for example, MnO4 minus needs H plus to be a oxidizing agent. And that is because if you look at your data booklet, permanganate, MnO4, needs to have the hydrogen ion present. So if it's not acidified, if that hydrogen ion is not there, MnO4 minus is not going to be an oxidizing agent because it doesn't have the reactants needed. All right, so our 5-step method to predicting reactions. However, here, our first step is, of course, we're going to have to read the question and list all the entities present and identify them as an oxidizing agent or a reducing agent. Now, after we do all that, so following the rules on the previous page, we're going to identify our strongest oxidizing agent and strongest reducing agent using our reduction of half reaction table on page 7 of our data booklets. Now, once we identify our strongest oxidizing and reducing agent, we're going to write the reduction and oxidation half reactions out as, of course, as per the table. We're going to balance the number of electrons, so basically just adding them together. And then, of course, step 5 is we're going to predict the spontaneity using spontaneity rules. So if OA is above your reducing agent, it's spontaneous. If it's the other way around, if your oxidizing agent is below your reducing agent, remember, it's non-spontaneous. So, of course, we're going to go over the first example here and the second one, and then hopefully by then you'll be able to open up your workbooks and go through the next few. So what we have right here is predict the most likely reaction occurring when copper metal is placed in acidified potassium permanganate solution. So our first step is writing out our entities. So just pay very close attention to the state of matter and, of course, the charge if we're writing it. So our first thing is we have copper metal being placed. So copper metal is not an ion, it's Cu solid. Now next is placed in acidified. So acidified means we have H+. Now potassium permanganate solution. Now just remember, solution means that there's H2O, but the fact that we have a potassium permanganate solution means that it is an ionic compound that is dissociated. So we dissociate all highly soluble ionic compounds into our potassium ion and our permanganate ion. And then, of course, because it's a solution, we got H2O liquid present. So that is step 1 in our 5-step method, writing out all the entities. Now we are going to have to classify them as oxidizing agent and reducing agent as well. So that means you're going to have to go to your data booklet here and try to find those entities as they show up on your data booklet. All right, so that means, for example, our first thing was copper, so we need to find where copper solid is going to be. Now we could use our general rule that we know copper is a metal. Metals generally lose electrons, so they're good reducing agents, or you can switch over and find copper right here as a reducing agent. So we know copper is a reducing agent. Then we look for H+. So same thing, we go to our data booklet and we go down and try to find our hydrogen ion, which we find hydrogen ion right here, which is on the oxidizing agent side. So we go back and label this as an oxidizing agent. Now, same thing is you're going to repeat these steps over and over. So you're going to find K+ is oxidizing agent, water is oxidizing agent, and our reducing agent. Now, one thing you will notice when you find the permanganate ion, and this is kind of mentioned up above, permanganate right here needs hydrogen in order to be an oxidizing agent. So in order to kind of show this, what you can do is show a little line, so linking two of these together and the fact that it's an oxidizing agent. So I'll try to keep that as the same color. So we have everything listed right here. Now it's just a matter of moving on to step 2 and identifying my strongest oxidizing agent and strongest reducing agent. So that's once again going to your data booklet, knowing our strongest oxidizing agent is closest to the top left, and we see our acidified permanganate is definitely up above, is the highest one there. Right, hydrogen's all the way down here, and water is even down lower than this, so water's all the way down here, and potassium's all the way down here. So we have our acidified potassium permanganate as our strongest oxidizing agent. So what we are going to do is list this. Acidified permanganate is my strongest oxidizing agent, and everything else I list as an oxidizing agent, I'm just going to scratch out. So next, I'm going to find my strongest reducing agent, which is either between water or copper solid. So same thing is we have copper solid right here, and we'll notice that if we try to find water as a reducing agent, it's going to be closer to the top, and it's up here. Now remember, as we go down, we get stronger reducing agents, so that means copper is my strongest reducing agent when compared to water. So same thing, I'm going to make sure I highlight copper as my strongest reducing agent, and knowing that water can't be a reducing agent. So I have my strongest oxidizing agent and strongest reducing agent. So I'm going to have one half reaction, my other half reaction, and of course when we add these together we're going to get our redox reaction. But before we get that, so we are still going to have to use our data booklet again. So our strongest oxidizing agent of our acidified permanganate reaction. So when we look at the entire reaction, we have our acidified permanganate. So we're going to take this entire thing right here and copy it over, right? So that means we have MnO4 minus aqueous plus 8H plus 5 electrons produces Mn2 plus 4H2O. So that is my reaction. Now as for the copper solid, now when we look at our data booklet, you'll notice I chose copper solid and it was just down here. Oh, that's cobalt. Copper solid's right here. Now for this reaction, because we're using on the reducing agent side, we're going to have to read it starting here and read it this way. So we're starting with copper solid, we're producing 2 electrons and copper 2 plus. So that's where you just have to be careful about how you're reading the reducing agent reactions or writing them down. So we're starting with copper solid, we're producing 2 electrons and Cu2 plus. Now, of course, we are going to have to add these reactions together. So that's when we get into step 4. We balance the number of electrons. I'm writing out the net ionic equation. So in our top reaction here, we have 5 electrons. Down here, we have 2. Lowest common multiple is going to be 10. So I'm going to have to multiply this equation by 5. I'm going to have to multiply my top equation by 2. Now, as for the coefficients, you can kind of stick them in as well, where we're going to get 2 Mn2 plus, we're going to get 16 H plus, we're going to get 10 electrons, 2, and our last thing here, our water, that 4 gets multiplied by 2, so we're left with 8. And same thing with our coppers, our new coefficients, we got 5 copper solid, we are going to get 10 electrons, and then 5 Cu2 plus. Now when we add these together for our redox, the only thing that is going to cancel is our electrons. So we got 10 electrons as a product, we got 10 electrons as our reactant, so they're going to completely cancel out. And our redox, we got 2 MnO4 minus plus 16 H plus. It doesn't really matter what or where you put these in. I can list the copper solid first if I want to. It doesn't really matter. As long as the coefficients are right in front of everything, you're golden. And that is our reaction. Now, of course, last but not least, we have to figure if it is going to be spontaneous or not, which when we're looking at back here, we have our SRA down this low. We got our SOA here. So our strongest oxidizing agent is above our strongest reducing agent. So this reaction is spontaneous. And that is the 5-step method to predict our reactions. So there's 2 more examples on the next few pages. So if you do want to challenge yourself, I would recommend pausing the video and trying example 2 on your own, see if you get it. But I'm going to, same thing, go over example 2 step by step as well with step 1, 2, 3, 4, and 5. So example 2, we have predict most likely redox reaction when chlorine gas is bubbled into an iron 2 sulfate solution. Now, when you're reading questions stuff like this, like the whole thing about being bubbled, remember chlorine is a gas, so the only way to get a gas to react inside of our solution is you have to find a way to get the gas into it. So really it's just connecting a hose into it and bubbling it through the solution essentially. But how we solve this will be the same. So our entities, we're going to list those first. So we have chlorine gas. So chlorine is an elemental diatomic, so Cl2. It's bubbled into an iron 2 sulfate solution. So same thing as a solution means that the iron 2 sulfate completely dissociates, where we have Fe2 plus. Sulfate is SO4 2 minus. In solution, we got H2O. Now, as for these here, determining if something is going to be an oxidizing agent or a reducing agent, same thing. You kind of want to go through, use your data booklets over here and see if you can find them. All right, now I would, oops, didn't mean to do that. I forever lost the data booklet. Oh, I'll get that back. But either way, so we have our Cl2 here. Now, pause the video and see if you can find all these here, but once you go through, you'll find chlorine is an oxidizing agent. We got iron 2 plus is a reducing agent and an oxidizing agent. SO4 minus pairs up with H2O to be an oxidizing agent, and water is a reducing agent and our oxidizing agent. Now, of course, when we do find which one's strongest, I'll pull up data booklet here now and show you. All right, so you'll notice that our chlorine gas is our strongest oxidizing agent, and our strongest reducing agent out of everything that is listed is our iron 2 plus, right? Because as a reducing agent, we have water that's all the way up here, right? So that is not the strongest, so we are not going to worry about that one. And then, of course, our sulfate and everything like that won't work either. So we have our strongest oxidizing agent is chlorine, and our strongest reducing agent is our iron, which means that iron won't be an oxidizing agent, SO4 won't be an oxidizing agent, and water won't be an oxidizing agent or a reducing agent. So we can start writing our half reactions. So strongest oxidizing agent, half reaction, and we're just going to write it exactly how it shows up in our table right here, and we're reading it from left to right. So we got Cl2 gas plus 2 electrons produces 2 Cl minus aqueous, and then of course for our strongest reducing agent, which is our iron half reaction. And remember, we have to read it backwards, so we're reading it from right going to left. So we start with Fe2 plus, we're producing an electron, and then iron 3 plus. So we got Fe2 plus is producing Fe3 plus, and then plus an electron. Now, of course, for our redox, we're going to have to get our electrons to balance out, so that means we're going to have to multiply this equation by 2 to get our new coefficients in front. Our iron 2 plus is going to be a 2, 2, and a 2. So now the electrons cancel out, and what we are left with is Cl2 gas plus 2 Fe2 plus produces 2 Cl minus, and then plus 2 Fe3 plus. And of course, we do need to determine if this is spontaneous or not, and we have our strongest strongest oxidizing agent above our strongest reducing agent. So this is indeed spontaneous. All right, so that is example 2. Now we do have example 3 there as well. So I would like for you to try to work through that one right there. But I will kind of post the answer for example 3 up in about 3 seconds. So for our third example, this will be the solution for this one here. So the entities listed all out are right here. Strongest oxidizing agent, reducing agent, half reactions right here. And of course, our redox reaction will look something like that. Now, same thing with 4. This right here, we have what will happen if tin 2 nitrate and acidified iron 2 sulfate are placed into a beaker. So this right here, so if you kind of want to fast forward and just look at the reaction, if you want to pause it and try this one, please go for it as well. But this is just another one of those ones I am going to go over just because it can be a little tricky. This right here, so our entities listed, we got tin 2 nitrate, so we got SN2 plus, NO3 minus, is in an acidified iron 2 sulfate, solution. Alright, so this is everything right here. Now, when you go through your data booklet and figure out if something is an oxidizing or reducing agent, we're going to get tin 2 plus is both an OA and an RA. Our nitrate and hydrogen ion together is an oxidizing agent. Iron 2 plus is an OA and an RA. Sulfate and water make an oxidizing agent, and water is an oxidizing agent and a reducing agent. So you'll notice that there's a lot of stuff going on in this reaction. Of course, hydrogen ion by itself is an oxidizing agent. Now, of course, when we're going to find out, like, everything here is potentially an oxidizing agent, so you just need to be able to find the strongest. So that means when you're going through your data booklet, you do have to be very careful at which ones you find. So I always like to start on the top left and start going down through it and find which ones I see first. And one of the ones that you're going to come across first, is this one right here. So we will notice that our nitrate ion, when mixed with hydrogen ion, becomes a really strong oxidizing agent, which is stronger than our tin 2 plus, which is down here, stronger than our water and everything else. All right, so our acidified nitrate ion is our strongest oxidizing agent. So of course, when we do write this reaction in, we are going to copy and paste exactly how it shows up right here. So that's what this reaction looks like when it's written out. So we just take it exactly letter for letter or word for word as we go through. And then of course, we can scratch out all of the other ones potentially being oxidizing agent as well. Now, as for our strongest reducing agent, so we do have possibilities of tin 2 plus, iron 2 plus, and or water. So same thing, normally it's good habit to kind of start down at the bottom right and start working your way up through and which ones you come across first. So you will notice iron shows up here, but this is iron solid, not iron 2 plus. So you're going to have to keep looking, right? So you go up through and then you'll find the first one that you see is the tin 2 plus. And remember, when we write this reaction, it is going to have to write it from right to left. So we write it in reverse. So we got tin 2 plus producing 2 electrons in tin 4 plus. So of course we add 2 of these together and we will notice the electrons already match up. So you scratch those out and we have our redox that looks something like this. And of course, this is a spontaneous reaction. So this right here, of course, it is a little trickier just because of the acidified nitrate ends up reacting and not the tin 2 plus and not the iron. So nothing in the iron or sulfate really does anything. It's just the acid. So that's why this one was a little trickier. But as long as you do write the entities in your careful how you list your oxidizing agents and reducing agents and finding them on your chart, you should be fine. All right, so that is it for the 5-step method. Our next lesson is going to be on oxidizing agents, so that'll be next week. And of course, you should definitely work through your workbook and try to get these down as quick as you can and try many of the examples that's there. All right, I'll see you guys next week.